Okay, let's start. Thought I escaped the flu, but I was wrong. So take it easy. Okay, continue with 6.6. I recall where we were last time. I think we butchered the graph for sine inverse, but that was the graph of sine inverse. We also looked at the graph of cosine inverse. It's like that. And the output for these guys, remember, was between pi over 2 and minus pi over 2. And the output for this was between 0 and pi. We also had y equals tangent inverse. This one was, domain was everything's like a big S, and it has a horizontal asymptote of pi over 2, and of minus pi over 2. So in terms of the graphs, I kind of just drew these for completeness, but you don't really actually need to know them. However, I would actually recommend that you do learn the graph for tangent inverse. It's the guy that we can still ask a lot of interesting questions about. So for example, if we want to talk about infinite limits and we want to evolve trig functions, usually we're going to be talking about this guy because these guys do not go on for infinity. They're very stuck in a very little box, and so they don't give us many options for interesting questions, but this one does. So tangent inverse is it's a very important graph, and you want to know what its limits are. You should also know the domain and ranges for all of these guys. So this minus 1 to 1. But they were all the rules that we spoke about. Inverse functions from previous sections still apply here. They just are the inverse functions for the trig functions, so they reverse them once you're within a certain range. Because the trig functions were not one-to-one everywhere, so we had to cut off a little section to create these functions, and that's kind of where we left off. So today I just want to give you a little bit more information about these functions, and we're going to learn how to differentiate them. In learning how to integrate them is a little bit more complicated, and we'll do that in the next chapter, but the derivatives we can derive. So maybe I should talk about also notation. These are the inverse functions. This can write the range over here. So there's the sine inverse of x. Again, remember that's just notation. It does not mean 1 over sine. It means the inverse function of sine. Sometimes to avoid confusion, you might hear this called arc sine, ARC sine of x. You might see that in a textbook from time to time or in other sources. Just don't be confused. It's just another name for this because this notation is confusing with the negative exponent. And we also know that the output here is only from minus pi over 2 to pi over 2. So we have cosine inverse of x. This is the arc cosine. This guy only works when your y value is between 0 and pi. It will only give you an output between 0 and pi. x or arctan. This guy will only give you outputs between minus pi over 2 and pi over 2, not inclusive. This basically means if you want to get answers outside of this range, then you have to use reference angles, and all students take calculus and all that stuff. But naturally, they work there. Then there are the other guys. We're not really going to use these guys very often. I'm going to tell you about them anyway. So the arc secant, arc cosecant, arc cotangent. In terms of things you can expect to see and be asked about all the time and actually use in other contexts, when we get to like integration and things like that, the main three are really the most important. They're kind of the ones I expect you to remember. And in terms of the graphs, the tan inverse graph is the one I expect you to remember. The other ones, not so much. Okay, so. This is the range of the secant, the cosecant. So these are very limited functions in general. You can't, their outputs will not give you everything. So it's something you want to be careful. Especially if you're ever using your calculator or something like that. You should always be aware that if you're using like an inverse trig function to find an answer, you'll usually only get an answer that corresponds to one of these two quadrants, and if you want another answer, you have to be aware that you have to actually do a little bit of work for it. But as I said, these three are the most common ones we need to know about. And yeah. In particular, this is really for completeness. I mean, usually this will be clear. The inverse functions, they only kind of undo each other in certain ranges. So we know that f inverse of f is equal to f inverse of f of x is equal to x, except for trig functions, it only works in these ranges. If you're plugging in the sine inverse, that's equal to x from 2 minus 1 and 1. Let's do some examples. Let's make sure we actually know how to find some inverse trig values. Probably still a bit of recap from a couple classes ago, but let's just make sure we're all on the same page here. Let's find sine inverse of a half. Sine inverse of minus 3/2. sine inverse of x and tangent sine inverse of x. Let's find a limit. A. How do you find sine inverse of a half? What do you think the answer is?
Pi over 6?
That one is pi over 6, since we know that sine of pi over 6 is 1/2. And that's basically all there is to it. So you remember that whenever we're doing this, we can have our little table in the side here. That's our theta, this is our sine theta and our cosine theta. This is pi over 6, pi over 4, pi over 3, 1, 2, 3, 3, 2, 1, square root everyone, and then divide everyone by 2. And of course, the sine of pi over 6 gives you a half, so the inverse function is going to take a half and bring you back to the pi over 6.
So,
That one, yeah.
sorry, do we only do pi over 6? Can we do like pi, that and? Do we do like 5 pi over 6? Because does it work at 5 pi over 6?
Okay, so that is a good point. And so let's actually say why not something like sine inverse of a half is 5 pi over 6. Because again, trig functions are involved. There are several answers. Yeah?
Is that because we like restricted the...
Exactly, because we restricted it, right? Remember that our sine inverse function can only output values between pi over 2 and minus pi over 2. It will not return any values outside of that range, right? So it only works, your sine inverse function only works in the first quadrant and the fourth quadrant. So all answers that will give you a negative sign, you want to pick them up in the fourth quadrant between minus pi over 2 and 0. And then all guys will give you a positive sign will be condensed into the first quadrant. So your sine inverse would never actually return a value of 5 pi over 6. So and that means if you are in a context where the answer you would want to know is the 5 pi over 6, it's an extra consideration for you. Right? It's something that you'd have to use like the geometry of the situation or something else to figure out. But the function itself will never return 5 pi over 6. It's outside of the range. What about this one? Minus radical 3 over 2.
Half pi over 3. Is it now in that fourth quadrant?
Okay, so here's how we think about it. We know from the table, what gives us radical 3 over 2? We know that sine of pi over 3 gives us radical. Right? But we want negative. Right? So then you go here. So you know this is the answer, this is where the pi over 3 is. Right? But which angle do we want? Well, remember our sine inverse only works over here. So if we're going to get a negative answer, we want it to be this one, right? We want to be this guy right here. Okay, so you wouldn't take, for example, someone over here. You also want to be able to express this angle in a magnitude that is between minus pi over 2 and pi over 2. So what could you say that that angle is? Yeah?
Minus pi over 3.
Minus pi over 3. Right, minus pi over 3. So essentially you start at 0 and you start counting negative. You can also take advantage of the fact that because sine is odd, this doesn't also always work, but it works here. Whenever you're in the right range, you can remember that sine inverse of negative x is just the minus sine inverse of x.
I just want to clarify that in the table,
Yes.
sine 1/2 has no correlation to cosine radical 3 over 2. It's just to the top.
Yeah, sine of pi over 6 is a half.
Yes.
Yeah.
But it has no, like the sine and the cosine above each other, like they have no correlation to each other?
No, you read the sine outputs are here and the cosine outputs are here.
Okay.
Technically they don't mix together.
Okay.
But the sine of an angle is always the cosine of its complement. I mean, that's always going to be a relationship, but yeah. So yeah, that, okay.
So you have to do negative pi over 3 since it's only in those two quadrants, like,
Yes.
so
So
you
if
couldn't
you
say
said
5
something like
over
5 pi over 3 or 4 pi over 3, you'd be incorrect.
Okay. Even though like 5 pi over 3 is in that quadrant, you just can't get to it in a way?
Right, because your function doesn't go that far.
Okay.
Right, your sine inverse function looks like this. It never actually outputs anything above pi over 2 or anything below minus pi over 2. So when you're saying like 5 pi over 3, you're up here. Your function actually can't attain that. So it's a technicality, something you have to be careful when working with these functions. And if you're actually computing anything in a calculator, you have to remember that the calculator is going to assume that there are these restrictions there. What about cosine inverse of minus radical 2 over 2? Now one thing you want to remember about the cosine inverse is that guy works in the top two quadrants. Meaning, if the value here is negative, you really want to take it from the second quadrant. Where if the value is positive, you want to take it from the first quadrant. So you're going to look at all your angles in terms of their magnitudes in one of these two quadrants. Okay? So we know cosine of pi over 4 equals radical 2 over 2. This means we want reference angle 4 pi over 4 in second quadrant. Second quadrant because we have a negative output. So this means cosine inverse of minus radical 2 over 2. What would that be?
3 pi over 4.
3 pi over 4. Right? And again, this all comes down to you cutting up that circle. You know, pi over 4 means you cut this into 4 sections. You want this one, so that's 1, 2, 3 sections. So that's actually 3 pi over 4 is the answer. Yeah.
What again is the reference angle?
Oh, reference angle is just the angle that's closest to the x-axis. So the reference angles are here, that's the main, here, here, and here. So those are the guys that will give you the base values. Need to get a move on. Okay, how do we do this one? You guys remember how to find and I want you to represent this as a function. You guys remember how to do that? Well, I'm going to remind you. Okay, so let's say you want to find the cosine of sine inverse of x. One way is to just set the sine inverse of x. You know it's an angle, so you set it equal to an angle. This would mean that x is equal to sine of theta. You can think of this as x over 1 to be very suggestive. You can then draw a right angle triangle. Remember that sine is opposite over hypotenuse. So this means the hypotenuse has length 1, the opposite is x, and therefore by Pythagoras' theorem you can find this guy, that's going to be 1 minus x squared. And so this means that cosine of sine inverse of x is really just the cosine of theta, because my sine inverse of x is theta. Cosine of theta, I can just go for it by this triangle here and do adjacent over hypotenuse. So it turns out if I take the cosine of the sine inverse function, it ends up being the expression radical of 1 minus x squared. I mean, that's important. We're going to use that like as soon as we finish this stuff. But so this was just for extra practice. So we'll do the same thing. Set cosine inverse here equal to theta. This would mean that x over 1 is equal to cosine of theta. So now you have the triangle where you have adjacent over hypotenuse. This side is 1 minus x squared. And so this would mean that tangent of cosine inverse of x is the tangent of theta, which is going to be opposite over adjacent. How about something like that? Yeah?
I have a question.
Yes.
Why do you put x over 1 for equals to cosine?
For emphasis, because we know SOHCAHTOA, so we know that cosine is adjacent divided by hypotenuse. So I'm just writing it as a fraction to emphasize that. I'm thinking of the x as the adjacent side and 1 is the hypotenuse. It's an emphasis thing, it's not really. What do you think that limit is? Yeah?
Pi over 2.
How'd you get it?
Because if you look at the graph of the inverse of the tangent function, it's an asymptote when it comes to pi over 2, so as it approaches 3.
Yeah, but what is this approaching here? Well, the top is approaching 3, but what about the denominator? Yeah?
0.
It's approaching 0, but what's the sign? As in SIGN.
Negative.
It's going to be slightly negative. So it's not quite 0, it's 0 with a negative charge. Because this guy's getting closer to 3, but he's getting closer to 3 from the left. Right? So that means he's slightly smaller than 3, so it's like 2.9999999. I subtract 3, I'm going to get a slightly negative number. So this guy here is essentially, we can think about as negative infinity. So now you have that picture in your head and you want to take that tan inverse graph and you want to go to the negative infinity. And so, turns out that is minus pi over 2. So how about derivatives? Recall, we actually know how to take derivatives of inverse functions. We could just actually derive this from scratch, but it would be essentially recreating the same steps, so we might as well just use the form that we already have. We know how to find the derivative of an inverse function. What was the formula?
1 over f1 of f inverse of x.
So now, using this, we will derive. Let's find the derivative of the sine inverse function. So here, my f of x is equal to sine x, and so my f inverse of x is going to be sine inverse of x. So we want the derivative of f inverse of x. This is going to be 1 over f prime of f inverse of x. This is 1 over, what is f prime? Derivative of sine is? Cosine. So I'm going to take the cosine of f inverse, which is the sine inverse. And there you get an expression, the cosine of the sine inverse. And what's the cosine of the sine inverse? Well, we derived that earlier. That is the radical of 1 minus x squared. This means that the derivative of sine inverse of x is 1 over the radical of 1 minus x squared. Which is a strange answer, probably. So the derivative of an inverse trig function is not a trig function at all. It's kind of this very weird radical function. But yeah, of course, by the chain rule. We know we can write down a general rule here. The derivative of sine inverse of u is going to be u prime divided by the radical of 1 minus u squared. So recommend remember that. You remember this, but this one, the chain rule variants are always nicer to remember. If you remember them, you remember the other ones. Let's get my black markers. Note this off. So we have the following. Let's see which one's the assay remembers. Well, I wrote all of them here, but no, I don't think all of them are important. Okay. So the derivative of sine inverse of u is u prime over the radical of 1 minus u squared. Asterisk beside that, I'd expect you to memorize that. The derivative of cosine inverse of u is actually just the negative of that. Right. It has this nice symmetry. The difference is when you're taking the derivative here for the cosine, you'll get a negative sign. So usually in applications where this one is useful, you don't need to know that one because it's not going to make much of a difference. There's just a sign difference. So maybe I'll put a double asterisk here and one asterisk here. The derivative of tangent inverse though, that is something I expect you to remember, double asterisk on that one. Single asterisk means I might ask you on a quiz at one point, but I'll probably never ask you again. But double asterisk, it's something that will come up repeatedly, even in the future, not even just in this section. This is u prime over 1 plus u squared, right? And all of these guys are derived very similarly using this formula and then playing around with the trig functions over here. So those are definitely important to know. Here are the other three inverse trigs. Them you'll probably only need like to do your homework. I probably won't ask you about them. But these ones are very useful, not just in this section, but when we get to integration. Because they have some forms that integrals are, they like to get themselves into this form. Like integrals you're going to do in this class, usually if you do a substitution, they're not going to maneuver themselves into one of these forms. But things will often maneuver themselves into these forms. They naturally arise. So it's going to be important. Let's actually find some derivatives here. A. y prime look like?
Negative 5 over square root of 1 minus 25x squared.
Exactly. That's your, in this case, 5x was your u. So 5x here was the u, and so you're going to put minus u prime over the radical of 1 minus u squared. Okay, yeah, not bad. B. What is y prime?
Negative 2x over a radical 1 minus x squared whole square.
Not much to do here. The most of the work comes in memorizing the formulas. Once you actually have the formulas memorized, it shouldn't be too bad. This one.
12x.
Hmm?
Oh wait. 4 times 12x
4 times
12x cubed all over 1 plus 3x fourth squared.
yeah. So this would be, what was that? 40x cubed over 1 plus 9x. Where was I going? Shit. So I prime.
2x sine inverse 4x plus x squared plus 1 times 4 over square root of 1 minus 16x squared.
Just want to make sure you guys still remember that the product rule is a thing. What about this one? How do you find y prime?
Implicit differentiation.
Implicit differentiation, okay. Derivative of this.
1 plus dy over dx
Mm-hmm.
over square root of 1 minus x plus y squared plus y prime equals 2x. Common denominator, I don't know.
Subtract.
Subtract what?
I was gonna say subtract this y prime, but there's no y prime in both.
How do I isolate the y prime?
Multiply the entire thing by rad 1 minus x plus y squared to get rid of the denominator.
You can
Sure,
pull out the y
we could
prime.
do that, but, I mean, that's okay, we could do that. I was thinking of just splitting the fraction up here. You know, just leave one of them and group the fraction over there, but we could do that. We can multiply by 1 minus blah, blah, blah. So you have 1 plus this plus y prime times this. And so we can subtract 1. Factor out a common y prime, we'd have 1 plus this. And here we'd have 2x times this minus 1. And so our y prime would end up being 2x 1 minus x plus y squared minus 1 all over. And that would be our derivative. And that ends today's lesson. So again, good thing to know here, but we're mostly going to care about this section for what it means for us for integrals, as it turns out. But you should know how to find derivatives. Those will come at some point. But yeah, so tomorrow we have a quiz and we'll start. The homework for this is due tomorrow. We have a quiz tomorrow and we will start the next section, which is hyperbolic trig functions.